So hello everyone, so welcome to this tutorial. So in the last session we are discussing about the introduction to the number systems, and we have seen the basic conversion of number systems from a decimal to other number systems. So in this tutorial we are going to continue this the number systems with the conversion to binary. So let us switch back to our screen here. So as you can see, the binary, as you can see here, we are looking into the binary to octal. So octal is nothing but it consists of the 8 numbers or 8 digits. So that is nothing but it range from 0 to 7. So if you want to write this equivalent binary, so it requires 3 binary bits or 3 binary digits also I can say. So 3 binary bits will keep on changing in this fashion. So 0 replicates 000, 1 replicates 001, then 2 is 010. Likewise it will continue 111. So this is the binary to octal equivalent numbers for 0 to 7. So likewise, just remember that it is a power of 2. Now for example, there are, with 3 bits I can represent 8 levels, or it is the reverse way you can also see. So this is a question mark. So 2 to the power of how much will result in 8. It means I have 8 levels here. So how many bits are required? So you can do the cross calculation for this to find out how many binary bits are required for this 8 digit or octal number. So likewise we will see in the next case where when we talk about the hexadecimal. Let me give the quick introduction for that also. So there in hexadecimal we have 16 numbers or 16 digits. So 16 numbers. So to represent 16 numbers, how many bits are required here? So 2 to the power of how much will result in 16? So that we have to find out. So based on that we have to choose those many number of binary bits. So let me clear this section. So let us take an example and see how to convert the given octal number to a binary number. I'll put this aside, this entire thing. Yes. Let's take an example here. So let us see, we have given with a binary number here, say 1 0 1 1 0 1 1 0 0 0 1 0 point 1 0 1 1 1 0, something like this. Some number is there in terms of binary like this. So this is in binary. Okay. So we have to convert this to octal number. So how can we convert this to octal number? See, the main thing here you have to consider where is the decimal point. So here is a decimal point here. So from the decimal point we have to group here from the left side. We have to go towards left side and group in terms of 3 bits. So this is 3 bits. What is this? This is from the table you can see 0 1 0 is nothing but 2. Next group another 3 bits here. So when we group this another 3 bits here, so 1 0 0, it is from the table, it is nothing but it is 4. So let us group this next another 3 bits here. So this is nothing but 5, and the last 3 bits if we group, so we will get here another 5. So likewise we have to group it, and we can convert this binary to octal. Now point, the decimal point is here, so write the decimal point. Now from the decimal point to the right side we have to go from this decimal point starting from the right to it. So now start grouping from the right 3 bits. So this is nothing but again 5. So next group another 3 bits. So I'll group it and we will write here this is nothing but 6. So finally this number is nothing but it is 5 5 4 2.56. This is to the base 8. Now let us take another example here. So I'll clear this. Hope you have understood this example. Any issues, please ask right now. Okay, let me shift this. I'll not delete it. I'll shift this here. So let me take another example here. For example, I'll take 1 0 0 0 1 0 1. Okay, point 1 0 1 1 0 1 1 1. So I will need to convert this number to octal number. So how do we convert this to octal number? Again we start from this decimal point to the left and start grouping from the left here. So I'll group here 3 bits. So this is nothing but my 5. I got. So I read this as 5. So next I'll group another 3 bits from my left. So then this is 0, 0. So this is 0. So now there are only one digit or one bit is left out. So there are no other 2 bits to group it. So what we have to do, so if there are no bits left out, so we have to add it on to the left as 0. So let me clear this bracket here because it is not required. So if there are no bits here to complete this format, so what we have to do is we will add zeros to its left and then we will group it. So now this is nothing but it is 1. So now likewise from this decimal point, let us group to the right in 3 bits. So this is, you put the decimal point here. So now this is 101 is 5. Next again 101, again this is 5. Now there are only 2 bits here, there is no third bit. So what we will do is we will add 0 to the right. Remember, we are adding 0 to the right, not to the left. So when we add 0 to the right and when we group it, we will get this as 6. So now the final converted result, it is 105.556. So this is in terms of octal, right? So hope you have understood. So now let us please read this as 0. It is not 6, this is 0. Okay, now let us look into the conversion from octal to binary, how to do it. So I'll erase this section here. Now for that, let us take an example here. So some number, it is 52734.634. So this is my octal number. I need to convert this to binary. It's very simple. So we need to write this equivalent binary numbers here. So what is 5? You can start from this one also, from the decimal point, it's fine. So 5 is nothing but it is 101. So 2 is nothing but 010. Now 7 is 111. 3 is 011 and 4 is 100, right? After that, put the decimal point. Now 6 is nothing but 110 and 3 is 011, 4 is 100. So this is how we will convert the octal number to binary, right? So like this you can work out any example. So just take a random number and you can find it. Now let us switch to the conversion of binary to hexadecimal. So now, as I said before, so it is a power of 2. So here there are 16 digits in hexadecimal. So starting from 0 to 9 and starting from 0 to 9 and A to F. So we have 16 digits. So 2 to the power of how much will result in 16? Can anybody tell me? So that is nothing but it is 2 to the power of 4 is equal to 16. So likewise we can calculate like n number of levels and how many bits are required for that. So now I require 4 binary bits to represent the hexadecimal number. So let us look into the example here, and I hope you know how this table is written. So it is in the same way like how we written octal. Only thing is that the one more level of bits here that is added. So if you want to write this in terms of the bit level, so let me shift this up. So actually this is written as B0, this is B1, this is B2, and this is B3, the bit positions. So I had no space at the down, so I had written the remaining two E and F equivalent binary on the right side. So now let us look into this conversion here. So I'll move this entire thing. Right. Okay. So let us look into the conversion of binary to hexadecimal. So again, let us say we have some binary number here, say 1011 1100011.1011101. So this is my binary number. So I have to convert this to decimal. So it's the same rule applicable here also. So from the decimal point, you start grouping in terms of 4 bits. So previously for octal what we have done, we have grouped into 3 bits because 3 bits will form an octal number, but here the 4 bits will form the hexadecimal number. So start grouping in terms of 4. So what is this? This is nothing but 3. So next group another 4 bits. So this is D. This is D, and you see here, so we are left out with no bits to group it. We have only 2 bits left out. So what we'll do, as usual, we will add 2 more zeros to the left. So when we add 2 more zeros to the left, now we can group it into 4 bits. Now this is nothing but 2. Even if you don't add, it is logically 1 0 means it is 2. So now for the decimal points, so again from the decimal point we start grouping in terms of 4. So this is nothing but after point, this is 1011. So this is B, and for this we have to add zeros here, and you will see only 2 bits left out here. So we will add the 2 bits to the right. Okay, and when we group it, you see that we got this as 4. So now the final result is, it is 2D3 dot B4 or point B4. So this is to the base 16. So if you look into the vice versa case, so if you want to convert a hexadecimal number to binary, so for example, let us take some example here. I'll shift this, move up. So then I'll take this example here as say any number you can take. So 2a, 2ac, then 8, then 4 point, I'll take it as EB. Okay, so this is a hexadecimal number to the base 16. So I want to convert this to binary. So how do we convert to binary? So what is the binary equivalent of 2? So binary equivalent of 2, now we have to write in terms of 4 bits. Now it is 0 0 1 0. So A is nothing but 1 0 1 0. C is 1 1 0 0. 8 is 1 0 0 0. 4 is 0 1 0 0. Dot or point, I'll write it below because I may not have the enough space here. Okay, I have the space, I can continue. So it is E is nothing but it is 1 1 1 0, and B is 1 0 1 1. So this is the total binary equivalent number of this hexadecimal number. So hope you have understood how to convert this binary to octal and hexadecimal numbers. So in the next we're going to talk on the complements of all these number systems. So let me save this and go to the new page here. So we'll talk on the complements. So first one decimals. Next, the second one, I'll talk on octal. Then third, it is hexadecimal. Then fourth is binary. So in each of these cases, there are 2 types of complements. Now, for example, in the decimal, if I talk, so again in decimal there are 2 types. One is the tens complement. We call it as tens complement, and here we have nines complement. This here is spelling mistake. So likewise, octal also has the 2 complements, that is the maximum value -1 and then its maximum value. So then here we have that as 7's, 8's complement, and then we have the 7's complement. So likewise here we have again 2 types, that is 16's complement and 15's complement. And in binary, we the mostly used two, that is of everyone are aware of it, that is 2's complement and 1's complement. And here it is 1's complement. So now let us see one by one what are these complements means. Now a tens complement means, now for example, let us take a number here and we want to find the tens complement of that number. So for example, 2, 4, 5, 9, 8. 2, 4, 5, 9, 8. So this is a decimal number here to the base 10. So in this decimal number, I want to convert this to tens complement form. So how to convert this to tens complement? To convert this to tens complement, how many digits are there? 1, 2, 3, 4, 5. So I have to subtract this from 5 nines, this number. So 2, 4, 5, 9, 8. So I'll get here as the answer as 7, 5, 4, 0, 1. So after subtracting, this is the answer I will get, and finally I have to add an additional 1 to its least digit. So I'll get here, this is final answer as 2, 4. So I'll read this as 75402. So this is the tens complement form of this number. So basically this tens complement is nothing but, for example, if we consider a circle here and we say this is 0, this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry. I'm supposed to talk only about 0 to 9. Okay, so now these are my decimal numbers from 0 to 9. Now for example, we have 1. If what is the binary, the tens complement form of 1? So I have to subtract that 1 by 9. So I'll get this as 8. So 8 plus 1, I'll get this as 9. So it means I'll go the 2 steps back. So from 1 it is 1, 2. So that is the tens complement form. Sorry. So minus 1. So basically when we talk about the minus 1. So minus 1 means we will go from the 0, we will go 1 step back side. So I'll get minus 1. So likewise, if we say minus 2, then okay. So here is like this. So for example, I want to find a minus 1. Minus 1, tens complement is 9. So how do we see that? Let us convert back. So 9 plus 9, what do we get? 18. So we have to discard this 1. So add this plus 1. So I'll get here 9. Sorry, not adding. I have to convert it back to sorry. It's not that. It's not that. Not adding. We have to subtract. So again the same process. So 9 minus 9, what do we get? We get 0. We add 1. So we get back our 1, right? So it is plus 1. So same thing. It means if I want to find the tens complement of minus 1. So tens complement of minus 1 is nothing but it is 9. And if you convert this back 9 to the actual form plus 1, or if you want in the actual form, so I'll get back my 1 here. So this is how we will do it. So this is the tens complement form. This is basically used in the subtraction method. Either we'll use the tens complement method or the nines complement. So basically tens complement is that, so whatever the number is there, we have to subtract first with 9 and then add 1 to its last digit. So that whatever the number you get, that is in a tens complement form, it means it is in a negative form. See, basically in digital circuits, how do we represent as any negative number? So digital circuit will not tell you anything. It will give only the values in terms of 0 or 1 or combinations of zeros and ones. Now if you want to represent any number that is a binary, so how do we represent that as a binary? So then we use these kind of techniques to represent that number is a binary number, because there is no sign representation in digital circuits. No value is written as this is +1, this is -1. So that is again represented in terms of binary values. So that is in a different form, negative form, so that we have to read it like in complements form we call. So let us take the next example. That is, next example is the nines complement method. What is the nines complement? So nines complement method is, let me clear this section here. So hope you have understood this. We'll take the examples later. So this is just to understand what is this nines complement and tens complement. So once you understood this nines complement, tens complement, then we will use this in the subtraction method. So then we can understand what is it means actually. Now let us take the nines complement. For the same number, if you want to convert to nines complement, then it will be less than the this thing. So now what we'll do, we'll take again same 5 nines here. So take the 5 nines and subtract this by this number here. So what do we get? We'll get the same number as before, 7 5 4 0 1. So previously what is the answer we got? It is 7 5 4 0 2. So there in tens complement we get the difference of one number. If you see, this is the nines complement and this tens complement, there is always a difference of 1, because in the previous case we added in the LSB bit, in the last bit digit as 1. So that is why there is a difference. So this is how we can convert this to nines complement. So this is your nines complement method, right? So likewise, eights complement and sevens complement in the same way. So now let us take a octal number here. So octal number 6 1 2. So let us take this as an octal number, and for eights complement we have to subtract this with what is its maximum number, that is 7 in octal. So there are 3 digits, so take 3 sevens. So subtract this number by 7. So what is this you will get? So here I will get this 1, this is 6, so here I will get this as 5. So now since it is 8's complement, so I have to add 1 to this last bit. So here I will get this as like this. Now the final answer here it is 166. So likewise, if it is just 7's complement, then I have to stop my calculation at this point and in order to add this 1. So that is your 7's complement and 8's complement. Hope you understood. So now let us talk on the 16's complement and 15's complement. So let me take a number here. So let us take me as 8AC7. So here the maximum number is F. In case of hexadecimal, so I have to take 4 F's because there are 4 digits. So subtract this by F first. So AC7. So when you subtract this, so you will get the answer like 7 5 3 8. And to obtain, this is your 15's complement answer. If you want 16's complement, we have to add 1 to this. So I'll get this as 1 3 5 7. So this is our 16's complement answer, right? So now let us take a binary number and let us see this. So binary, we will take any number here. So it is 1 0 1 1 0 1. So I taken this number. So now the maximum number in binary is 1. So first take all ones. I'll tell you the another method for 2's complement. It's very simple rather than doing subtraction like this for 2's complement. So what we have to do is you convert wherever 1 is there to 0 and wherever 0 is there to 1. So this is 0. This is same as subtraction with all ones. So this is 1. So this is 0, 0, 1, 0. So this is your 1's complement answer. If you want to convert this to 2's complement, you add 1 to the least LSB digit. So 1, 1, 0, 0, 1, 0. So this is the 2's complement answer. Fine. So hope you have understood. So now we will look into the subtraction, then you will understand how this is useful. I'll clear this section. So binary addition, hope everybody knows it. So let us take some binary number here and perform some addition. So 1 0 1 1 0. We need to add this with say 1 1 0 1 0, something like this. So we know the binary addition. So 0 plus 0 is 0. 1 plus 1 is not 2. It 0 carry 1, because the maximum number in binary is 0 and 1. So when it becomes both 1, so we know that it becomes 2. So 2 in binary it is represented as 1 0. So it 1 goes to carry here. So it is 1 plus 1 plus 0. So again it is 0. So again there is a carry. 1 plus 0 plus 1. So it is 0. So again 1. So 1 plus 1 plus 1. So what do we get? So it is actually 3. So binary equivalent number in 3 is it is 1. So one more carry here. So there is nothing to add. So this is 1. So this is our final answer. That is 1 1 followed by 4 zeros is the answer. So now let us look into the subtraction. I'll clear this. Let us take the subtraction here. So just take any number 1 0 1 1 0 1 and 1 1 0 1 1 0. So I have to subtract this number. If it straight away subtract this number, so there is a method to subtract this. Either we can go for 1's complement method or 2's complement method. So let us look into the 2's complement method. So this is basically called as the subtractant. It is a subtractant, and this we call it as the miniand. So subtractant should be converted to 1's complement. So what is the 1's complement of this? So this is 0 0 1 0 0 1. So it is in a 1's complement form. Since we are performing the 1's complement subtraction, so then after that we will add this with the miniand. So miniand is 1 0 1 1 0 1. Add this complement number here. So it is 0 0 1 0 0 1. So then we will get this as 0 0 1 0 1 1. So this is the 1's complement answer of this result, the subtraction result. There is a 1's complement subtraction. Now if you want to perform the 2's complement subtraction, so let us take one more example here and I will show you the difference. I'll clear this. So I think so far it's not making much of its sense. Don't worry. When we look into the decimal subtraction, you will understand. So let us take one more example here, that is 1 1 0 1 1 minus 0 0 1 1 0. So now if you want to subtract this, so this second number or the subtractant we have to first convert it to 1's complement. So it is 1 1 0 0 1, and now we have to add this complement number with the miniand number. So that is nothing but 1 1 0 1 1 plus, we have to do addition here, so plus 0 0 1. So what do we get here? So we'll get here 0. So this is also 0 because here we'll get carry. So it is 0. So now it's 1. So it is 0. So carry 1. And here we will get 1 and carry 1. So in this case, whenever we get carry, we have to add that carry here. So we'll add this carry here. So then the final answer will become the carry should be added to the leastmost bit here. So it is 1 0 1 0 1. So this is the ones complement result. Now if same thing if you want to do with the twos complement, so now this is in the ones complement. So let me write here, I'll not confuse you. I'll write this here again. So let me take the 2's complement number of this subtractant. So I'll get this as 1 1 0 0 1. And you know that for 2's complement I have to add 1 to this leastmost bit, to the LSB bit. So here I'll get this as 0 1 0 1 1. Now I have to add this with the minion. Minion is this number. So let me add with this. So it is 1 1 0 1 1. Let us add this 1 1 0 1 0. So when we add this, we get this here 1, this is 0, there is a carry 1. So say this is, we are doing addition. So 0, there is one carry 1, and here we'll get carry. So in this case, whatever the carry we'll get, we have to neglect it. So our final answer is only this. So that is the difference between the ones complement and the twos complement subtraction. In twos complement, we should not add that number, we should discard that final carry result. And in case of ones complement, if we get carry, so that carry should be added to the LSB bit. So I hope you have understood this subtraction. Now we'll quickly look into the actual decimal number subtraction. I'll clear all this. So let us take, for example, I want to subtract 58 minus 34. So when I want to do this, so what is the actual answer here? So 8 minus 4 is actually how much? It is 4. So 5, this is 2. Now the answer is positive, so no issues. So now it is positive. Now let us say this, let us convert this number to binary. How do we convert this number to binary? As we know that we keep on divide this number by 2 and then we will get this to binary. So this is nothing but we'll get 29, its remainder is 0, and this is 2. So like this will continue, and I'll straight away write here. So this number is, I'll get this as 111010. So this is my 58. So likewise for 34, we will do the same method. So keep on dividing this by 2. I'll get this as 17 and the remainder 0. Then once again divide this and we'll get 8 and we'll get remainder 0. So we'll continue until we'll get the last less than 2. So then finally I'll get this as 0. Sorry, I'll get this as 1 0 0 0 1 0. So this is my final answer. So let me write these two numbers here, 1 1 1 0 1 0. So here 1 0 0 0 1 0. So now I want to subtract it. So how do we subtract? So we'll use the ones complement method or twos complement method. So let us use the ones complement method. So first I have to complement this second number. So to complement second number, take this as 0 1 1 1 0 1, right? So this is my ones complement answer. So now this I have to add with the minion. So minion is 1 1 1 0 1 0. So let us add this 0 1 1 1 0 1. So then I'll get answer as 1 1 1, and this is 0. So carry I'll get, so this is 1, so this is 0, and this is 1. As we all know, whenever we get carry, we have to add this to the rightmost bit. So let us add this. So the final answer is 0 0 0 1 1 0. Now if you have calculator, so convert this number and see whether we'll get this as 24 or not. So convert this number to decimal. So it's very simple. It is 2 to the power of 0, 1, 2, 3. So it is 2 to the power of 3 plus 2 to the power of 4. So 2 to the power of 3 is what? So it is 8 plus 16. We get 24, right? Yes, we'll get 24. So this is the right answer. So hope you have understood how I did this. This 2 to the power of 0 plus this multiplied with 2 to the power of 1. This is multiplied with 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, like this. Okay, so this is fine. No issues. Because this is a greater number and this smaller number, and we got the result as 24. So no issues. Now we are running short of time. Let me quickly do one more last example here. I'll clear this entire area. I'll clear this unwanted area here, and I want to show you one more interesting thing. So I'll clear this. Now let us reverse this case. Now for example, we want to subtract 34 by 58. What is the answer? So answer is minus 24, right? The answer is minus 24. So now let us do this with the same ones complement method. So now these values will get reversed. Now it means 1 0 0 0 1 0 will become your minion, and 1 1 1 0 1 0 will become your subtractant. Now we have to take the ones complement of the subtractant. So ones complement of subtractant is nothing but it is 0 0 0 1 0 1. So this is the ones complement number. Now we have to add this with the minion. So 1 0 0 0 1 0. So then let us add this number 0 0 0 1 0 1. Now let us perform addition of this. So this is 1 1 1 0 0 1. So there is no carry, so there is nothing to add, so we will left out with this final answer. Now if we calculate this in terms of decimal, so what do we get? That's 2 to the power of 0. It means it is 2 plus 2 to the power of 1 is 2 to the power of 0 plus 2 to the power of 2 plus 2 to the power of 3, 2 to the power of 4, 2 to the power of 5 plus 2 to the power of 5. Now can you quickly tell me, anyone, what is this? 2 to the power of 5 is nothing but 32 plus 4 plus 2 plus 1. So it is 36, 38, 39. So this is actually, rather than writing this as minus 24, the answer is 39. So 39 is the in terms of the 9's complement of minus 24, because in binary there is no way that we can represent this in terms of, say, negative numbers. So this is how we will represent the negative number. So okay then, thanks for watching this tutorial. So we'll wind up the session here. So catch me in the next tutorial.